Good afternoon, everybody. So unfortunately, our director, Professor Barone, cannot be present, and therefore it is my pleasure and privilege to introduce our speaker of today, Professor Tim Palmer, who is Royal Society Research Professor in Climate Physics at Oxford University in the UK. Professor Palmer got his PhD in General Relativity Theory, so he's a physicist from Oxford University. Then he moved into the field of weather and climate dynamics and prediction, first at the UK Meteorological Office and then at the European Centre for Medium-Range Weather Forecasts, where he was head of the predictability division. In 2010, he returned to Oxford as one of 2010 anniversary Royal Society Research Professors. He was elected as a Fellow of the Royal Society in 2003 and served on the Royal Society Council in 2008 and 2009. In 2011 and 2012, he was president of the Royal Meteorological Society. Now, to introduce more in detail about the research activity of Professor Palmer and on the topic of today's seminar, I will leave the stage to Roberto Wizza. Thank you.
Thank you very much, Chiara. So thank you very much, Tim, for accepting this invitation. I met Tim Palmer in 1991 when he actually interviewed me when I applied for a position to join the European Centre of weather forecast, where we worked together for many years, and it was a great experience. And then in 2010 he left, went back to Oxford University, and I continued essentially his area of activity. I just want to mention a couple of things. The team has been very instrumental in developing new approaches to weather prediction. So when under his leadership we started a medium-range ensemble prediction that provided probabilistic prediction to our users. It was one of the first, and it's still the best probabilistic prediction system of the world. He then started also a lot of activity in longer-range prediction, understanding how we could actually extract predictable signals from the atmosphere, from what are the sources of predictability, and he led to the implementation of a seasonal prediction system. So today, Tim is going to talk about climate predictability, so we're going back to an even longer time scale. Stochastic modeling, this is an area of work where we worked together years ago, and he's still doing a lot of research at Oxford University, and inexact computing. This is the link between these three areas of work is actually something that he started when he moved to Oxford University. So thank you very much for coming down to Pisa. It's my honor to have you here. Please. Thank you.
Thank you. If I speak like this, you can hear me, or? Yeah? Okay, good. I guess I normally start by saying it's an enormous pleasure to be somewhere like here. And it is in a way enormous pleasure, but unfortunately British Airways took the shine off today by one of its engines misbehaving, which meant we had to change planes, and then having changed planes we had to wait for a takeoff slot. And anyway, so I have to say I'm deeply impressed that there's still any audience at all, because it's now, I guess, 2.5 hours since I should have been starting. So thank you all for staying so long. I'm impressed. Yeah, so Roberto has introduced the title of the talk, and in a way this is going to be a rather broad talk about a number of research topics which I think have a common theme, and I hope the theme will be clear from well, at least at the end. But I want to start by making the point that all of this work is very much motivated by practical problems. And in fact, I wanted to start by just emphasizing the role that climate models let's call them weather and climate models, the two are somewhat indistinguishable these days, are playing and indeed will increasingly play in the future. I really think that going forward, weather and climate models will really be a crucial part of making society more resilient to extremes of weather and climate, not only those occurring today, but those projected to occur in the future with obviously increasing levels of greenhouse gas. So I just want to start by just putting a few bullet points on different but related topics. So the first is I call seasonal decadal prediction, which is in a way an extension of weather forecasting. We try to estimate the initial conditions for the atmosphere and the oceans as accurately as possible with observations, and then use the models to project forward in time to make regional predictions of, whether of drought or flood or anomalous warmth or coldness or storminess or whatever. And I think, as I say, this will increasingly be important, for example, in enabling humanitarian organizations to get aid into countries that will be affected by drought before the worst suffering happens. I think climate models will enable aid agencies and other organizations to become much more proactive rather than reactive going forward. Now, there's a number of topics which relate to, obviously, to climate change, and models are indeed the main scientific input into, global discussions on decarbonizing the world economy, such as Paris, because they basically tell us, what are the risks of not doing anything in terms of weather extremes around the world. But given that, climate has already warmed and we've already emitted a certain amount of CO2 into the atmosphere, CO2 is at 400 parts per million, pre-industrial at 285, so we've got a certain amount of climate change that's inevitable, and so the questions going forward that national governments will have to address and are addressing is what type of infrastructure do we need to invest in to try to adapt to these kind of inevitable climate changes. And again, that will need accurate and reliable climate models, accurate on the regional scale, to address those questions. And then there's this whole issue about is there a plan B, as it were, to climate change? Can we put in some kind of masking effect, for example, by spraying sulfuric acid droplets into the stratosphere to create sulfate aerosols, which then might reflect sunlight back to space and offset the effects of increasing carbon dioxide. Well, that's kind of an easy thing to do on the back of an envelope, but once you start to think about the problem, it's much more complicated, because you're offsetting a problem in the, if you like, infrared part of the energy spectrum, the fact we're trapping heat. We're offsetting that by reflecting visible and ultraviolet light back to space, so it's not quite doing the same thing. And the question is, does that have any unforeseen consequences? And the thing you could conceivably imagine is that, for example, that this shield above in the Earth's stratosphere could have the effect of reducing the moisture supply to the rainforests in the tropics. Now, if that were to happen, and the rainforest started to die, then you'd end up producing a source of carbon in the atmosphere, which would be completely, the opposite of what you wanted to do. So if we're going to be at all serious about geoengineering, and I don't really think it's a serious proposition at the moment, but it might conceivably be, then we really need to understand these types of issues, the complex interactions that occur in the climate system as a result of some particular perturbation. Attribution of current weather events. This is a very popular thing, certainly in the British press. Probably, I imagine it's the same everywhere around the world. When you get some unusual weather event, the press immediately want to know what's caused it. whenever they phone me up, my first reaction is to tell them probably nothing caused it. This is the way the world is. You shouldn't necessarily think everything has a cause. But, you know, the question they're angling for is how much was caused by human climate change. And people are trying to develop techniques to do that in a sort of probabilistic sense. I think that's still ongoing work, but it's certainly a very active area of ongoing work. And then the last point is scientific understanding, which might seem slightly orthogonal to these other topics, except to say that I think if you're communicating with policymakers or decision makers, or indeed the public, if you actually understand what you're talking about, it makes life much easier. And I think they understand, they can sense when you don't really understand what you're talking about. So I think actually the whole issue of communication is, depends on good scientific understanding. So just having a model that produces X, Y, and Z, and you don't really understand why it's done that, is not a good place to be in. All right, so that's just a general issue about why climate models are important. What are climate models? I mean, broadly speaking, they're our best attempt to solve the underlying equations of the climate system. And I'm going to, I'm a physicist, so I'm going to sort of gravitate towards the physics of climate as in some sense being the most important aspect of climate. Sure, there is chemistry and sure there is biology. But we don't know, we don't even have equations for biology. So if we have biology, we have to represent it in an approximate way. But we do have equations for the basic physics of climate. We have Newton's laws of motion, which is expressed as these Navier-Stokes partial differential equations. We have equations for thermodynamics and then various conservation properties, which are all expressible mathematically in terms of, in this case, partial differential equations. But to solve them, we do what's called, or at least I am going to call the canonical numerical ansatz, because it's basically universal, which is to project the equations onto some sort of grid, some sort of finite discretization, and then recognize that computers are not big enough to represent. See, those Navier-Stokes equations basically couple everything from the largest jet streams down to molecular scales on the right-hand side. But, computers aren't big enough to do that, so we have to truncate somewhere. And then you get this duality, if you like, between the dynamic, the resolve part, the projection of the equations onto your finite grid. And then what are called parameterizations. They're simplified formulae to represent things which you can't resolve. And typically, as we'll come to see, convective cloud systems, orographic gravity waves, ocean mesoscale eddies. These are all things which can't be resolved, at least in current generation models. And so and I'll say a bit more about this in a few slides, but the technique is to try to find some kind of simplified formulae to describe these unresolved parts. I've written the resolved part, the dynamical core, as it's often called, in this particular talk, using a kind of a grid technique or a finite truncation technique, which is used at the European Weather Center and is actually relevant to what I want to talk about towards the end of the talk, hopefully time permitting, which is so-called spectral method. So what you actually project the equations onto are spherical harmonics, which, if you know about them, are just kind of wavy fields on the sphere. So those little circles, whatever you like to call them, are different spherical harmonic basis functions with different amounts of waviness. And as you go down from the top of the triangle represents the very largest mode, and as you go down, the wavelength gets shorter and shorter. So these are more and more sort of representing smaller and smaller scales. And by the way, just to say that in a model like the European Weather Center model, the right-hand side, you might be surprised to know, takes about as much time on a computer as the left-hand side. So it's not that these these formulae are so simple that they take a trivial amount of time to produce. The problem is there are so many aspects to the right-hand side. I've represented 3 here, but it's also radiation, how photons are absorbed and are emitted by the atmosphere. It's also things like turbulence in the boundary layer, many different types of cloud motions. And then you have a lot of other things to do with how to represent the land surface, how to represent sea ice or ice sheets, and so on. So there's a lot of so-called subgrid processes which take a lot of computing time. Just to say that before I further say, I'm just showing you here that if you said to a meteorologist, what are the basic sort of motions in the atmosphere, they would probably talk about 2 different types of things. The mid-latitude weather systems, which have scales of about 1,000 kilometers, and kind of cloud systems, which have scales maybe of a kilometer or so. Now, these are both energetically and thermodynamically important in the atmosphere. The large-scale weather systems basically transport heat from the tropics to the northern latitudes. They're a part of the sort of thermodynamic engine which pushes heat out into high latitudes where it's radiated back into space. Whereas these convective cloud systems, which are much smaller, serve the role, particularly in the tropical latitudes, of moving heat from the surface up into the free atmosphere. And in a sense, they're both modes of instability of the flow. But for whatever reason, nature has determined that these things are 3 orders of magnitude difference in horizontal scale, and that creates very serious problems for modeling them. And in fact, pretty much all of today's global climate models, or indeed even global weather prediction models, which because they only need to run for a relatively short time, can have a higher resolution, shorter grid spacing. But none of them really have enough resolution to resolve those convective clouds, nor indeed those waves over the topography, nor indeed those little eddies which mix water near the Gulf Stream and the Kuroshio in the Pacific. So that's why those things have to be parameterized. And of course, that means we're solving these Navier-Stokes equations well away from the kind of viscous scale at which they really extend. And it's certainly the case that people who are who study the Navier-Stokes equations from a very theoretical mathematical point of view would even question whether we are solving the Navier-Stokes equations, because the truncation is so far away from the viscous scale. So that's a kind of a slightly debatable point, but we're doing our best, if you like, to solve these equations as accurately as possible. If I can, I'm not sure this will work now, actually. Okay. All right, this doesn't matter. I just realized there was an animation which probably I needed to have copied another file over to, but we won't worry about it because I just want you to show, this would have been a movie of convective clouds looking at them from a satellite sitting way above over the tropical Western Pacific. And the point I want you to see is that these clouds are sort of rather heterogeneous. You get areas where there are sort of big blobs of clouds, other areas where there are no clouds, and some areas where there are lots of little clouds. There's a whole kind of spectrum of cloud systems going on there. And this is, it does work. Goodness gracious, there we are. So actually one remarkable thing is that out of this organization, you see 2, there's one and there's a second one about to form, tropical cyclones, which have this little, you can tell them by the dark center, which is this eye structure, which propagates across. Anyway, very kind of complicated behavior. Now, the reason I'm showing you that is that this notion of parameterization is sort of based on ideas in statistical mechanics. If people who've done courses on statistical mechanics will know that if you have an ensemble of small-scale processes, and many of them, and the processes are just occurring on scales much shorter, much smaller than your sort of macroscopic grid that you might be interested in, then under those situations, you can quite accurately describe the bulk effect of these small-scale processes on the large scale, on the macro scale, without having to worry about any individual process. You can do a kind of statistical average over a distribution and get a well-defined bulk formula. And of course, molecular viscosity and molecular diffusion is exactly that type of approximation, where you have a kind of Avogadro's number of small molecular processes within some macro domain. So the concept is, behind parameterization in weather and climate models, it's a similar sort of thing. So if we want to parameterize convective cloud systems, we somehow imagine we have lots of these little convective clouds such that we can aggregate all of the statistics together within a grid box and get a simple formula. The problem is that life isn't like that, and that animation was kind of supposed to illustrate that fact, that when you actually look at the real world, you see a spectrum of scales. You see a few small ones and maybe a small number of middle-sized ones and one or two really big ones, aggregated ones, within your grid box. And as I'll show you in a minute, this is consistent with what's called power law structure, which is itself a consequence of nonlinear scaling symmetries in the Navier-Stokes equations. So the fact you see something like this, rather than that sort of regular ensemble of small-scale processes, is actually a consequence of nonlinearity in the Navier-Stokes equations. And when I talk about power law, I mean this diagram on the left is a very famous diagram from some years, decades ago now, of observations in the atmosphere looking at how much energy there is, kinetic energy, as a function of horizontal scale. And it's drawn in a log scale. It's sort of, so you get this linear in log space. So what that means is it's not, if you had that, the kind of statistical mechanics picture of the world, you'd expect to see the energy kind of drop down to zero, and then there'd be nothing very much for several sort of decades of these logarithms, and a little spike at the end showing a lot of sort of subgrid energy at scales which are far removed from your macro scale. But instead, you see this rather steady decrease in energy. And in fact, there's this interesting shallowing of the spectrum, which is essentially due to the fact that as you get to smaller and smaller scales, the rotation of the Earth becomes less important, and that affects the dynamical properties. If I gave another talk, which I sometimes do, on Lorentz's butterfly effect, it's actually to note that what Lorentz meant by the butterfly effect is that if you have which is actually it's been completely misunderstood by not only the public, but most, I think, mathematicians. But what Lorentz meant by the butterfly effect was the fact that if you have a system, an atmospheric system, let's say, or a nonlinear system which has this shallow power law structure, like the atmosphere does on scales of 100 kilometers or less, then actually that will have a finite predictability horizon. You will not be able to predict beyond a certain finite time. And the reason is that if you make your errors smaller and smaller in scale, they actually just grow faster and faster. So in some sense, you can never reduce the error in your initial conditions enough to prevent the errors kind of saturating at some finite time. Formally, this hasn't been proved rigorously, and it's actually the topic of the Clay Mathematics Millennium, one of these $1 million Millennium Prize problems on the Navier-Stokes equations. All right, anyway, that's a slight aside. So I talked about models in general, how they're all formulated, and the question is, are they good enough today for the sorts of things I presented at the beginning, helping emergency aid agencies deliver goods, a season ahead of time? Or are they good enough to really know whether we can safely spray sulfates into the stratosphere? And I would say the answer to that is no. They're not actually good enough. There's a couple of quotes here. I think I'm going to just focus on the second one because I'll pick that up a little bit later in the talk. The first, and this is all, by the way, there's this kind of organizational structure in our community whereby all the modeling groups around the world do integrations, and they're put into what's called a model intercomparison project, and they go by different names, CMIP3, CMIP5. And people can look, you know, have things got better? CMIP5 was our most recent one, and people have looked, well, have the models actually got better than they were, say, 10 years previously in the CMIP3 ensemble? And the answer is actually, depressingly, that models have hardly improved at all. The top slide is talking about something in the tropics. Sorry, the top quote is in the tropics, which I'll skip over. The bottom one is a phenomenon which is relevant in this part of the world, and indeed my part of the world, which is the occasional occurrence of anticyclonic, persistent anticyclonic weather. We're actually, I mean, you know, certainly at the moment, this is a period of persistent anticyclonic weather. It's led in the UK to an extremely unusually dry and hot summer so far. But in winter, it also occurs when it's typically leads to very cold conditions, but also dry conditions typically. And models do generally very poorly at simulating these long-lived anticyclonic conditions, which is something I'll come on to. All right, I'm going to sort of slightly change gear for a few seconds to introduce something which Roberto talked about, which is ensemble prediction. So Roberto and I worked for many years at ECMWF and introduced the ECMWF ensemble forecasting system. So this is now, we're talking about just medium range 10-day, 2-week timescale forecasts. And I'm just showing I'm not going to show the forecast, but just show this very simple Lorentz 63 model, which just illustrates the point that if you're not completely sure about your initial conditions, then, and you have a very nonlinear, well, you have not a nonlinear system, then you can't assume that the errors you make at initial time will grow in the same way on every forecast occasion. And what this slide shows, if I can try this technology now, see if it works. Oh, it does, yeah, okay. So, takes a bit of getting used to. So this is showing how a little kind of ball, if you like, of initial error hardly grows, actually, in this Lorentz system when you start up here. But if you start a little bit further away, so the forecast trajectories go in a different direction, then the errors can become more substantial. And if you start somewhere else, then the errors can actually explode. And this is obviously important because it means that on the top left, you can be fairly confident about the weather. The bottom figure means you're not at all confident. And if you can estimate that ahead of time, that becomes very important information for people who might be making decisions based on the forecasts. So ensemble forecasting is really trying to estimate, I mean, more generally, it's estimating probabilities of weather, and the fact that in a nonlinear system, these probabilities are very flow dependent, even if the initial conditions are, the initial uncertainty is always the same every day. Now, we introduced this, last year was the 25th anniversary of it, but we realized pretty quickly that there's actually more than one source of error in forecasts, and one is the initial conditions, but the other is the sort of thing I've just been talking about, the errors you make when you try to truncate your underlying partial differential equations. And if you neglect that second source of so-called model error, it means that your ensembles become, if you like, too confident. They stick together, they stick to one another too closely. And then on occasions, you find that the observations, the verification lies outside the range of the ensemble. So a technique which Roberto and I and a third colleague, Martin Miller, worked on in the 1990s was, I mean, conceptually it was quite, I would say, quite radical, because certainly the philosophy then, and there's still little vestiges of this philosophy existing today, but hopefully rapidly disappearing. But the philosophy was that since the underlying equations are deterministic, then our models should somehow respect that and also be deterministic. But our argument was pretty much along the lines that I've talked about, that these deterministic parameterizations are really inconsistent with the underlying scaling symmetries of the Navier-Stokes equations. To try to pretend that you can represent the subgrid scales by a formula closed on the large-scale flow is actually inconsistent with the structure of the equations you're trying to numerically represent. So we propose really that as a sort of as a way around the problem, that the parameterizations should be treated stochastically. So in other words, treated as distributions that you sample from in a random way. So in that sense, even if you had absolutely identical initial conditions, then this would generate some spread in the forecast trajectories, because every time you'd be sampling a different from the distribution in a different way. Now, I'm proposing not to go into any great detail here, but we looked at, one way one can investigate this is to take a high-resolution model and treat it as truth, and then take a low-resolution model, and then ask how would you, if you wanted to develop a stochastic parameterization in your low-resolution model, which adequately captured the statistics of the high-resolution data within your low-resolution grid, how would you do that? And the main thing that came out of that type of study was that the stochasticity got bigger as the parameterized tendencies got bigger. I mean, that's not totally surprising. So in that tropical West Pacific region, that's where all this convection stuff is really going very, very strongly, probably more than any other part of the world. And that's where stochasticity turned out to be biggest. So the scheme that we developed is really just a, oops, that's the one, isn't it? There we are. So this is a stochastic term. This R is a kind of stochastic random number. And this x dot p is the parameterized tendency. This could be, x could be temperature, for example. Let's take its temperature. So temperature coming, say, from these convective clouds. So the bigger is this temperature tendency from the convective clouds, the bigger is this stochastic term. So this is like a multiplicative noise stochastic term. And one of the things that this immediately did was to radically improve the scores of things like precipitation in the tropics. So what you've got here is a sort of forecast skill score against forecast time on the x-axis. And the gray line at the bottom is the model without any stochastic parameterization. And the colored lines are different shades, different varieties of stochastic parameterization. But the main point is that there's about a 4-day sort of difference in skill between the model, the deterministic model, and the stochastic model. I sometimes I used to say to the ECMWF director that, typically ECMWF used to reckon its sort of improvement as roughly adding 1 day of skill every 10 years of work. And the ECMWF budget, let's say, was £50 million a year. So 10 years is £500 million. So 4 days is £2 billion worth of. So I used to say to director, or just give Roberto and me, we don't need 4 billion, but just give us like 4 million will do. That just as a small recompense for our. Well, that didn't work very well, but I don't think anywhere in the ECMWF code will you see so few lines of code having such a big impact. However, what I want to talk about is a kind of second aspect of stochastic parameterization, which has sort of got which has interested me in a sense more in recent years. And that's the effect it can have on the climatology of the model and some of these biases that I talked about early on in the talk. So I want to talk about a way of thinking about the middle latitudes, the northern hemisphere extratropics, in terms of what you might call quanta, or sort of discrete states of the atmosphere. And this is an analysis done by actually colleagues here in the audience, Susanna Corti, looking at the observed atmosphere in terms of what we call clusters or regimes. So these are quasi-persistent states of the atmosphere. So can we, if we were to diagnose, and this is particular to wintertime, can we kind of represent the way in which the atmosphere evolves from one week to another week to another week in terms of transitions between quasi-stationary states? And the answer is that it does look that that is a fruitful way of analyzing the real world. So this is an analysis of data of the real world. And what it shows are 4 distinct quasi-stationary states. This is in terms of a middle level flow, kind of a pressure at the middle level in the troposphere, expressed as an anomaly. I don't know how much the audience is kind of familiar with meteorology, but I'll just sort of, if I can do this thing again. Oh yeah, where are we? Yeah, let's take this one. This one here, that red blob over Northern Europe stands for essentially a big persistent anticyclone. So that's that blocking anticyclone that I talked about, which certainly affects Northern Europe substantially. This one here is what would be associated with a very strong westerly flow across the North Atlantic, and often leads in, say in the UK, to, if you have this persistently over a whole winter, it can lead to flooding along large parts of the UK, because you just get storm after storm sort of going through along the jet stream. So that's a very strong, that would correspond to a very strong jet stream. This one is one which is sort of the opposite, where the flow across the North Atlantic is much weaker. And there's a 4th one with a kind of anticyclone in the North Atlantic. I don't think I'll go into much more detail than that, except to say there's a kind of statistic here. There's a statistic here which tells you, in a way, how reliable this discretization into these 4 regimes or clusters are. And that 99.8% means statistically it's extremely unlikely that this just arose by some chance sampling of an underlying Gaussian distribution. Okay, now what's the relevance of these regimes? Well, my own view is, and I wrote about this some years ago now, is that these are really important to understand and make sure that models simulate well. If we're to understand, for example, how the atmosphere responds to climate change. And I want to illustrate that with a very simple, again, the simple Lorentz 63 model, where I've just added on this forcing term to 2 of the equations. Now you'll notice this equation, the Lorentz model has these 2 regimes, essentially. These are 2 quasi-stationary clusters, effectively. So the system goes around one or goes around the other and makes relatively rapid transitions in between. Now something quite interesting happens if you look at how that system responds to that, the Lorentz system responds to the additional forcing. So we're going to put the forcing, without going back to the last slide, I had a parameter theta which could vary the direction of the forcing relative to these x and y. These are 2 of the variables in state space. So that theta equals 0 means the forcing points along the x direction. The response of the system isn't along the x direction, it's along some sort of almost diagonal between x and y. All right, let's move the forcing to point now on that diagonal. and then the response is along the forcing. But now I'm going to put the forcing along the y direction. Again, the response, however, is in this diagonal direction. And even when the forcing's at right angles, the response is in that diagonal direction. So what's on earth going on here? Well, it turns out that diagonal direction is essentially the direction between the two regimes. You can characterize it as the leading empirical orthogonal function of the covariance matrix. But more importantly, it's the direction between the regimes. So what's basically happening is that when you force the system, the response is that one regime gets a bit more stable and the other regime gets a bit, if you like, less stable. So what your response is instead of the probabilities being 50-50, it's like 60-40 or 70-30 or something. And it's changing that, the regime, the probability of finding the system in one regime or the other, that basically determines the response to the forcing. So this is quite a nonlinear effect. It's something you wouldn't get from a linear system. And it means then that if you want to be confident your model is responding correctly to now say doubling CO2, in my view, you had better be sure that your model has this regime cluster structure adequately. Now, as we'll see shortly, models typically do poor. Well, we've already actually seen with the quote that the blocking anticyclone was relatively poor. But more generally, models do poorly at these regimes. And I've got a slide showing that in a minute. But what I want to show you here is another experiment you can do with the Lorentz model. And this is also, nonlinear systems are really fantastically beautiful, but they're also unbelievably subtle. And you probably wouldn't have guessed what I'm about to show you. So what I'm going to show you is taking those Lorentz equations as before, and now adding on stochastic noise. And the question is, how does the system respond to the stochastic noise? Now, you might think, for example, okay, you've got these regimes, but if you add noise, and the noise is just somehow a sort of Gaussian noise, it's just going to wash out the regime structure and make it less regime-like. But it turns out that at least for small amounts of noise, almost the opposite happens. So this is the top one is a time series of the. It doesn't seem to work now. Does it work? No. What am I doing wrong? Okay, not to worry. The top figure is just the standard Lorentz model without those red stochastic terms. But the middle one is with let's say, a smallish amount of noise. And I think you can see by eye, and certainly this could be, I could show you objective diagnostics which quantified this, but I won't bother this with you. You can see that the regimes actually become more stable. The typical residence time in a regime has actually increased. Now, if you increase the noise yet further, then what you might have imagined naively does happen, which is you tend to start to wash out some of this impact. But there's this kind of intermediate noise level where stochastic noise actually increases the residence time in a regime. You can do this with models which are actually more realistic representations of the atmosphere. This is the so-called, this is the barotropic vorticity equation written in terms of a geostrophic approximation. And this is, you can truncate, this is work that Charny Devore did some years ago, truncate the equations. Again, with topographic forcing, the model has a regime structure. But the interesting thing is, the two top slides, by the way, all this work is from Frank Kwasniok at Exeter University. The top two slides are sort of time series of two components of that Charny Devore model in standard deterministic mode. And then the bottom two are the same two variables, but with some noise added. And again, you see that the regimes have become much stabilized. We're trying to understand this. This is actually not an entirely trivial thing, and it seems to do with the fact that when the model makes a transition from one regime to another, it tends to make it along a very specific part of state space or phase space. And if you upset that transition, if you kick it out of that very low dimensional subspace, then that will upset this transition, and it tends to then stick around longer in the regime. It takes time to get back into, find its way back onto that exit route. Well, the interesting thing is that this seems to happen in climate models as well, and this was some work, again with Susanna Corti here, we did some years ago looking at different versions of the European Weather Centre model. Looking at this, well, the top slide, I don't know, again, does this work? No. Don't know why. The top one shows this P statistic. And I think I'm going to, so when P is close to 100%, the left hand, the one that says ERA, yeah, what am I doing wrong? Okay. So it's not me. I'll carry on talking. The top one, sorry, the left hand, if you look at the top figure, left-hand side, ERA, that's the observations. The P statistic's very close to 100%. If you were to look at the one on the, I'll just keep talking. If you were to look on the extreme right-hand side, it was from a kind of CMIP type climate model, and there the P statistic is very, very poor. It's 90%, meaning these regimes aren't significant. There's a T511 model, which is a sort of what would certainly be pretty much state-of-the-art climate, where it starts to get significant. But the T511 SP is adding stochastic parameterization, and you see it pushes up further, quite close to the 100%. So this kind of is an illustration of what we saw with much simpler models, that stochasticity actually can help improve this regime structure, which is crucially important in my view for climate change. I think I'm going to skip over this for lack of time, but this is some much more recent work which Susanna and colleagues have been doing, which pretty much kind of bears out this same result. Okay, I got, I guess, like 10 minutes or so. I don't want to keep people here long, because I know it's, I don't know if it was me, it'd be my dinner time by now. But I want to kind of talk about where this is all going, because, and I just wanted to talk about this last topic of imprecise computing. Just to sort of set the stage, I mean, I think that these questions, particularly the ones I posed at the beginning of the talk, are so important for society that, it frustrates me in a way that, although climate science is well funded, we need something like the vision of the European Weather Centre, which has done a fantastic job in medium-range forecasting for these longer-term climate problems. They are so important, and models are really getting so kind of complex these days that I think we've got to start thinking, for example, here in Europe, in a much more coordinated European way than we have in the past. I mean, by the way, I'm sick every day hearing about Brexit, so don't talk to me about Brexit. I don't want to know. Because Europe, for me, has, the European Weather Centre has been a fantastic example of what can be achieved with European collaboration. And I've written, papers over the years trying to propose, and CERN, of course, is another great example for high energy physics. We need something like this in climate change as well. Well, things have sort of come, starting to come into a little bit of focus insofar as the EU put out calls for the next flagship project. So these are basically 1 billion euros over 10-year type projects, the human brain being one that people have heard of, graphene, quantum technology is a recent one. So a group of us got together and put in a proposal called Extreme Earth, and it really, in a way, tries to, to say, right, let's develop the next generation climate models at a much more European level. And let's try to actually get rid altogether of these parameterizations for these key processes like convective clouds, orographic waves, ocean mixing. And this means getting down to 1 kilometer in scale. Now that will certainly require exascale computers, and not only that, dedicated exascale computers. And indeed, the whole purpose of the Extreme Earth proposal is to try to get enough funding that we can get dedicated exascale computers. But actually, if you do the calculations, just exascale itself won't be enough. We need to actually quite radically improve the efficiency of the code of current models. Typical models, the sustained speed of a climate model on a computer is really only a few % of the peak speed of a model. And the reason is because of all the parallelism, and moving so much data around really prevents one achieving this peak speed. If we could get peak speed on an exascale computer, then we could do it, but we need to overcome this problem. Now, stochastic parameterization will certainly continue to be important in a 1 kilometer model, because although we now will be able to resolve some of these key features, there will still be lots of turbulence where you're not resolving, and the same arguments will be relevant for parameterizing subcloud turbulence, for example, and the fact that it's necessarily going to have to be stochastic. But the point of raising this is that there is a second kind of role, if you like, that stochasticity is playing in this whole issue about designing more computationally efficient models. And I think I'm going to skip over that for lack of time, and sort of just probably reminding people that, of course, any variable from the partial differential equations has to be represented by some real number in a computer. And traditionally, in scientific computation, we've done everything in these 64-bit double precision representations. So you have 1 sign bit, 11 exponent bits, and 52 mantissa or significand bits. One of the things which has occurred in recent years is the move towards lower precision numerics, and it's been very much driven by artificial intelligence community doing computations at very low, many computations, but at much reduced precision. So a lot of chips these days, e.g. coming from NVIDIA and I think IBM and so on, actually have a capability of running code now at not only double and single precision, but even half precision. So either single being 32 and half being 16-bit. Now the point about this is that it's not just, in fact, it's probably the most important thing isn't the fact that you can do computations faster, it's that you don't move so much data around. The real energy overheads on exascale computing come from data transporting within the computer. Now, the presence of stochasticity in one's numerical model is telling you that globally, 64-bit precision may be very wasteful. And there's a fundamental question here, really, which is how much information, how much real information, how many bits in these variables carry real information. If we can reduce precision, then clearly we can reinvest our savings to do like increased resolution, this goal of reaching 1 kilometer. So I often, have this mantra that less precision could actually mean greater accuracy. This is a study that was done on a very idealized system by a postdoc in my group a couple of years ago. This is another Lorentz type model called Lorentz 96. And the model, essentially, you can imagine 3 different resolutions: a coarse resolution, a medium resolution, and a fine resolution. And this was run actually on a type of computer called the field programmable gate array. And the point about that is you can actually measure how much energy the computation takes. And we treated, because this is such an idealized model, we don't treat truth from the real world, but we had a high resolution double precision integration as our truth. And the curves on the left-hand side show how forecast errors against this high resolution double precision, very precise, very high resolution truth go. And it turned out that the model with the smallest forecast error was the one that had the fine resolution, but essentially 16-bit representation. But not only that, the actual energy that was being consumed, and the little chip, what's called chip area, sort of tells you how much energy, it kind of gives you a kind of a visual picture, if you like, of the energy being taken in doing the computation. The model that had the highest accuracy actually took almost an order of magnitude less energy than the one with the biggest error. So this is quite a nice, simple example of how this could work. So a colleague of mine, Peter Dubin, who's now at the European Weather Centre, coded up the ECMWF model in single precision. And in fact, most of the work ECMWF does now, trying to explore this, kind of getting towards this 1 kilometer goal. We can run the model for a few days at 1 kilometer, but it can only be done at single precision. And his claim is that that makes there's no degradation in performance, degradation in skill, but it almost speeds up by a factor of 2 the code. So in Oxford, we've been trying to sort of look at this a little bit more, and this is where this spectral technique actually turns out to be quite interesting, because with spectral techniques, you can make the precision scale dependent. So you can make the high wave numbers, the very small scales, which are most strongly affected by the stochasticity and the parameterizations, you can make them less precise. And they, of course, dominate the computational load of the dynamical core, because there are so many of these high wave, and it's this big triangle which is bottom heavy. So we've done tests where we ramp down the precision as the wave number increases. So I'm just going to show you, just for fun, I hope again this works, an animation of this iconic Hurricane Sandy. ECMWF, I should say, or to be more precise, the Europeans, everyone here, got a lot of credit for this storm, because the Weather Service, the US Weather Service model, predicted the storm would head out to sea, whereas the ECMWF model, as you'll see, had it tracking back over New York from where it started over the Caribbean, Florida region. And the Washington Post and New York Times picked up on this, and there were lots of headlines for several days. Why are the Europeans so much better than we are at weather forecasting? And what they meant was, why is the ECMWF model so much better? So this has become, I have to say, the National Weather Service has done quite well out of this storm, because they said, well, it's because we don't have as much investment as those Europeans do. And then the Congress gave the Weather Centre lots of money to build a new model with a new computer. Anyway, what I want to show here is, though, I've got 3 animations just before I start. So the left is the sort of canonical double precision one. The right top is single precision. And the left, we've gone down to 8 bits in the spectral part of the dynamical core. So it's really down at this half precision level. Now the question is, I challenge you, you can look at any one you like. I challenge you to see any difference between these 3. So here they go. And what you'll see is they all have this wonderful ability to track back the thing the American model couldn't do and hit New York. They are. So they're all pretty identical, but one is with dramatically reduced levels of precision in those significant bits. Okay. All right, I'm just going to I'm going to go through this extremely briefly, because the other, but I do want to say it, because the other way we think we can get a big increase in computer speed is through this, really developing area of artificial intelligence. But there was some really seminal work done at ECMWF by Frédéric Chevalier 20 years ago now, using just one layer deep neural nets trained on output from the radiation parameterization, the thing that models the emission of infrared energy back to space, which is very complex parameterization. And he developed a one-layer neural net, which took about an order of magnitude less computational time than the full parameterization. And this result from his paper, all you're to take from this is that each of those two graphs are skill scores, and there are two lines on them, one with the expensive radiation calculation, the expensive radiation calculation, and the second with this neural net, and they lie on top of each other. So I think I'll come to a conclusion. So I have talked about the importance of the importance of climate models, but the fact that current generation models still have substantial biases and systematic errors. Stochastic parameterization actually can help reduce these biases, and I've talked about their role in in blocking, if you like, blocking anticyclone, more generally regime-type structures. But it's also brought very much into focus the fact that our kind of default double precision representations of variables is probably wasteful and inefficient, and that's going to really hurt us as we move to this exascale era where we're really trying to get as much as we can out of these computers to get to a 1 kilometer grid. And my own view or hope is that the next generation models, they'll be ultra high resolution, they will get down to this 1 kilometer scale, but they'll be typically single with perhaps large parts even in half precision, and with stochastic neural nets on the right-hand side. So that instead of having 50%, taking 50% of the computation, they'll take 5% of the computation. But they'll be trained on output from state-of-the-art parameterizations, and they'll be trained offline. They'll be trained, in a non-time critical way. So I think this is an exciting time for climate modeling. The state, I should explain, of this framework project is we've put in a bid which got through the first round towards what's called a preparatory action, where you spend a year writing the full proposal. So we're hopeful we might get to that stage, but it's anybody's guess. But and if anyone here has any influence with the European Commission, the name was Extreme Earth, and it's a great project, right? That's it. Thank you very much.
Thank you very much, Tim. Thank you very much for a great lecture. So, are there questions for Tim? Who wants to start the first question? I'll start with one question. At the beginning, you touched on chemistry and the physics of the atmosphere. Here at the school, they do a lot of computational chemistry, and my question is, when do you think we will need to add chemistry to these climate models to improve them?
I mean, a lot of these questions, depend on what time scale you're interested in. For example, the carbon cycle becomes certainly important once you go beyond, you start talking about 100 or more years into the future. So having an interactive carbon cycle probably is not so important on short time scales. The other crucial question about chemistry is, can you run a chemical model offline? I mean, for example, if you're trying to estimate the impact of changing circulation patterns on some particular chemical species, which itself is has no great impact on the reaction back on the atmosphere, then you can run that offline. The issue becomes when does chemistry start to feed back onto the atmospheric circulation. I mean, stratospheric ozone is a good example of something which certainly feeds back very strongly. So it's kind of a difficult question to answer. I would certainly say going beyond, a century, chemistry and biology are really extremely important. I would say for things like, seasonal to decadal prediction, I think if there probably are areas where you need some sort of chemical representation, but I suspect that these can be done in a relatively simplified form, and that's always the crucial question. Getting this balance between spending computational time on the thing that's really important, and not spending so much time if it's of secondary importance. I mean, that's really going to be the crucial question going forward. So I would say for most of the extreme Earth applications, chemistry, there will be a role for chemistry, but overwhelmingly the sort of real driver has got to be the physics and the circulation patterns.
A question from the audience? Yeah. Can you say who you are and where you work, please?
Yes, I'm Franco. I work I'm a chemist here at the Scuola. I work with Professor Barone. So my question is, one problem I think that climate and weather modeling has is that, contrary to other sciences, it has to deal with the public more because of policy and climate change. So when you start adding stochastic modeling and results, that makes things even worse for people to actually understand what it means to predict something. So is there any work that is being done on how to actually explain to people what type of results that you can get and what it means when they talk about climate change? Because then, of course, people go to vote and that can have consequences.
Yeah, I mean, I suppose, the general framework, if you like, for this whole area is what you might call risk analysis. So, a country might, for example, if this is a question about food security, so you want to know what is the risk of complete crop failure because of, temperatures that are too hot to sustain the crop growth or lack of water, in a way that is the trying to say, well, the risk of these things has increased by a factor of 10 or 100 or something, or whatever it is. That's a way of, I think, putting over the idea that this is potentially a serious problem that has to be taken into account, while still at the same time expressing things in what is essentially a probabilistic way. So, I mean, that is a challenge, of course. We have to be scientifically honest. So I think being, overly deterministic is not, in the long run, going to be beneficial. But, I'm always encouraged by, for example, in medium range forecasting, which I've talked about. I mean, one of the things which now I think is pretty much second nature to people who live in the path of hurricanes is that they get from from pretty much on the TV now, they'll see this kind of what they call cone of uncertainty, which is basically an ensemble sort of distribution of possible tracks of the hurricane. And, people just understand now that you can't predict precisely where the hurricane's going to be. And in a way, it's for you, or maybe it's for the town, the city mayor or something, to decide, is that risk big enough to evacuate the city or whatever. So this framework of risk analysis and decision, under uncertainty, decision on the basis of risk, is so kind of generic now that, it covers pretty much everything from, to tomorrow's weather to climate change. And I think to be honest, half the problem is that the meteorological community has been in the past much too deterministic in its communication. And so people now sort of expect that. And when you back off and you say, well, actually we've got to treat things probabilistically, they think you're, you're sort of somehow, you don't know anymore. Well, actually, no, we're just trying to be more honest. And I would criticize the people who were more deterministic in their outlook for giving the public that perception that this is the way things can be done.
Okay, are there more questions from the audience?
Yeah, one at the front.
Yep.
That was an excellent lecture, of course. Thank you for this. It was an honor. You mentioned that the ANN models are not being operationally used.
Sorry, which ones?
The neural net.
Oh, neural nets, yes.
Would you please explain why you think this is happening, or what we could do to make them become more operational? Because to me it sounds, just to give you the background of the question, like a natural solution to a doubly, if you want, nonlinear problem. So on the one hand you have the nonlinearities of the basic physics, which you identified very nicely, and at the same time you have nonlinearity of the mathematical solution, the numerical side. And that is, in a very naive, easy to simplistic description, may be the reason for the problems we come across right now so far. So a neural net, which is a naturally nonlinear approach to, based on the data, as opposed to a preconceived perception of the world, a model, seems like a pretty natural, progress in this direction.
Well, I think things are ramping up as we speak. So this is certainly an area where there's a lot of interest these days, and I'm sure we'll see something becoming operational within a few years. I mean, the guy Frédéric Chevalier, who did this work 20 years ago, I mean, he was kind of ahead of his time, unfortunately, and people, he was a single person working on this, and unfortunately, I think the work was fantastic and probably could have even got in then, but whatever reason it didn't. But there is a debate. I mean, since you raise it, and I'm sort of a little bit on the fence on this, because the way I phrased it was to train the neural networks on the parameterizations, which I think is a fairly safe bet. The more radical approach would be to actually train the neural nets on observations. The problem there is, do you have enough observations? Can you really isolate, physical processes adequately? I think, I'm kind of aware that whilst neural nets have a lot of promise, there's also a lot of hype in the world, and when I think about the physics of trying to go direct from observations to kind of a unified parameterization concept, I worry. And I have to say also, I worry because the whole purpose of several of my bullets was to talk about the future. So if you train something only on things that have happened now, they're not going to necessarily be reliable in the future. On the other hand, you can run your parameterizations in a sort of what's called a single column mode with double CO2 and whatever CO2 you like, and those neural nets can be trained on these future radiative profiles and things. But that's an area of I would say uncertainty at the moment, and I don't know, we'll just have to see how it plays out. But for sure, it's going to be important, and I'll just say, as a sort of people who are cognoscenti at the ECMWF, I think this also has great potential for speeding up 4D VAR and the minimization loops in 4D VAR. If you put neural nets into the tangent, linear, and adjoint models, that will make a big difference to the cost of 4D VAR.
Okay, very good. I think I would like to give a final round of applause to team. Thank you very much for the lecture and the time.
As I say, thank you to all of you for staying at such a ridiculously late hour.
Okay, have a good evening to everyone. Thank you. Thank you for coming.
Yeah.